Okay, we'll get started. We're going to be talking about 9b, which is going to be Coulomb's law. So it's going to be a law that describes electric forces. So, as previously stated in 9a, the force of a field increases as you get closer to the center of whatever is making the field. So, for example, if I had a positive charge, electrical charge, and then I had, I don't know, maybe another positive charge. The positive charge is going to create an electric field, and what's going to happen is if you move those two charges closer together, the force is going to get stronger and stronger. So again, that's true for electric fields. That's true for other types of fields too. So that's true for gravitational fields too. So again, remember, I don't know, if we had maybe a planet, Earth, and then we had the moon. It's the same idea. There's going to be a field, basically not electrical this time, but gravitational fields that are surrounding each object with mass, and you're going to get a gravitational force because of that. I know that's how it wasn't described exactly like that before, but that's really what's happening. So in objects with mass, there's going to be gravitational field, and the interaction of that gravitational field is actually going to cause a gravitational force in a very similar way to how electric charges create an electric field that creates a force. So I think it's going to make a little bit more sense once we get a little bit more into it. So you've actually, again, it wasn't described exactly this way, but you have experience calculating the gravitational force that's a result of that gravitational field, and it's right here. This is Newton's universal law of gravitation. So that describes how strong that force of gravity is as a result of basically the interaction of that gravitational field. So again, remember that big G was a constant. You had the two masses, and then you had d, which was the distance between the two objects. So again, that was mathematically how we can calculate the gravitational force between two objects that basically have mass. So we're going to be looking at an equation similar to this for an electric field. How can we calculate mathematically the same thing with an electric field for an electric force? So we'll go to the next section. Here we go. So just like we had the Newton's law of gravitation for gravitational fields, we have another law for electric forces that would be a result of an electric field. So we're going to call that Coulomb's law. Coulomb. So Coulomb's law is an equation used to calculate the electric force between two charged objects. And again, it's right here. It's very similar to the Newton's universal law of gravitation. I'll write that out again. So this is the universal law of gravitation. This is the the Coulomb's law. You can see they look very similar. And we're going to go through each part of what the electric force is referring to. So again, this equation is if you had maybe like two positive charges, what would be that electric force? What would be the size of that electric force between them? So Fe right here, like I said, that's the electric force. And that's going to be measured in newtons like every other force. Right here, the Ke, technically, that's Coulomb's constant. That's going to be 8.99 times 10 to the 9th newtons times meters over c squared. So that's going to be always the same number, basically. That's never going to change, much like G from the Newton's law of gravitation. And then we have the two charges over here, Q1, Q2. Those are the charge of each object. So if we have two charged objects, you have Q1, Q2. It's just how big the charge is for each object. And charge is going to be measured in coulombs. C for coulombs. So again, 5C, 5 coulombs. And again, the two charges very similar to the two masses, Newton's law of gravitation. And then the last part, d, the distance between the two objects measured in meters. So that's a description, the distance, that's a description of how far these two objects are away from each other. Very similar to what's in Newton's law of gravitation. So that's all the parts of the law. There's just the last thing to keep in mind is the notation, or for what a positive and negative force means. So let's think about if you have two positive charges or two negative charges, when you multiply them in the numerator, when you multiply the two q's together, q1 and q2, when you multiply them together, if you have two positives, you multiply them, you're going to get a positive. If you have two negatives, you're going to get a positive. So it's basically saying if you have like charges, you're going to get a positive force out. You might get, I don't know, positive 5 newtons. So again, if you get a positive force basically at the end, then you're looking at a repulsive force. You're looking at a force that's going to force the charges apart. Like right here, this, if you had two positive charges, this would be a repulsive force. Same thing it would be with two negative charges. In the other situation, if you had, so again, when you're multiplying q1, q2, if you had two negatives, or sorry, negative, positive, positive, negative, you'd get a negative force out in either case. So you might get something like negative 5 newtons when you're doing out the equation. If that comes out negative, then it's going to be, you're going to have an attractive force. So again, if you have two, I'll just draw quickly right here. If you have a positive and a negative, whoops. So if you have a positive and a negative charge, these two are going to want to pull towards each other. And again, you'd have an attractive force, and the math is going to come out so with the equation, so the force at the end is negative. So that's Coulomb's law. Again, there's a fair amount of stuff here, but the important thing to remember is it basically says how it lets you calculate the electric force that's caused by an electric field. It's very similar to the force of gravity, the way it's calculated. So some very similar setup. What Fe is, what Ke is, what both the Q's, what D is, and then the notation for what if you get a positive number out, that would mean the force is repulsive, or they're trying to push the charges apart. If it's negative, that would mean it's attractive. So that's Coulomb's law. That's the basics of it. We're going to get into a problem I think that's going to help a lot with making sense of it. So where is it? Here's the problem. So take a second, read it, see if you can do it first before I go through it. Okay, so we'll go through this problem. So what we have is we have two negatively charged identical spheres. Sketch it out here. Position 3 meters apart from each other, okay? And then there's a 5 Newton electrical force on each other, basically. So they exert 5 newtons on each other. So is the force attractive or repulsive? So let's think about this as the first thing. So we have two negative charges. That's going to be, those are like charges, so you're going to have repulsive. So opposites, or not opposites, same charges are going to repel, repulsive. So what's going to happen is you're going to have electrical force like this. It's going to be the same size of the electrical force, basically. I don't know, we might call it 1 and 2. The size of the electric force is going to be the same on either one. But it's going to be, they're going to be going opposite directions, basically, because they're both repulsive, because they're the same sign of the charge. Now B is asking, okay, what's the charge of each box? Whoops, should say sphere. Just pretend that's a sphere. So we got to calculate this. So what we're going to do is, if we want to deal with force and relating force to charge, we're going to look at Coulomb's law. So we got Fe, Ke, Q1, Q2 over the distance between them squared. So what do we know? We know the force between them, and it's going to be the same. We know the Coulomb's constant, that's always the same. we don't know the charges, but what we do know is if they're identical, they're going to be equal to each other. So we don't know what it is, but we do know because they're identical spheres, they're going to have the same charge in this case. So in this case, Q1 is going to be the same as Q2. And then D, we do know. We do know how far apart they are. So we're ultimately solving for what's Q1, Q2, which we know are the same. So let's start plugging in. We know the force, electrical force is 5 newtons. We know the K is 8.99 times 10 to the 9th. Yes, I'm not going to write out the units. And we know Q1 and Q2 are the same in this case, so we're just going to call that Q for now. That'd be fine. So Q times Q for the charge. And then the distance between them is going to be 3 squared. So let's do out the algebra. We're going to have 45 is equal to 8.9. We got 8.99 times 10 to the 9th times. So Q times Q is going to make it a little simpler. Q times Q is like X times X, same thing. So it's going to be Q times Q is going to be Q squared. So again, what I did was I multiplied the 3 squared by the 5 to get the 45 by itself. So we're going to do this next. So what we're going to do is if we do this out, 45 divided by the 8.99 times 10 to the 9th, we're going to get a really small number, 5 times 10 to the negative 9th is equal to Q squared. And then if we take the square root of that, we're just going to get Q, and Q is going to be equal to 7.07 times 10 to the negative 5 coulombs. And we got to remember it said they're negatively charged, so it's going to be negative 7.07 times 10 to the negative 5th C for coulombs. So that would be how to calculate the charge. So again, that's the problem. What we're doing, we took 2 charges, we realized that they're repulsive. We're calculating the charge of each of them by using Coulomb's law. And that's about it. Make sure you have this down.